All right, so this is our second and last lecture on Chapter 4, Two-Dimensional Steady-State Conduction. We talked about the shape factor, conduction shape factor. I'd like to talk about it right now and solve a problem. So the conduction shape factor was cap S. What units did it have? SI units. Meter, because it's really an area to length ratio. Think of it as the area to length ratio. So if we have a zone or a face or a point or a region that is a constant temperature T1 and another zone, a point, a face, a region, a constant temperature T2, there will be some motivation for heat to flow from 1 to 2 if T1 is higher, and it'll flow at the rate proportional to the thermal conductivity and the shape factors. So there's our equation. The rate of heat transfer is the product of thermal conductivity, the shape factor, and the temperature difference that drives the flow. So let's solve this problem. We have a 20 by 20 by 30 centimeter box. It has a uniform surface temperature of 0 degrees C and is covered by 2 centimeter thick insulation. So think of the inner box as I'm not very good at sketching 3D, and then we have insulation covering it, and the thickness of that insulation is what? 2 centimeters. So if you went to the outside dimension of the box, it would be 22 or 24 centimeters. Which would it be? Instead of 20 centimeters, what would it be? 22 or 24? 24, because you have thickness on both edges. So 24 outside by 24 outside by 34 outside, right? So that's what we have, the inner box and then the outer box. It's insulation in between. The thermal conductivity of the insulation is given, and the temperature on the outside is given to be 30 degrees. So 0 degrees temperature on the inside, 1 is 0 degrees C, or if you want to call that T2, and then T1 on the outside is 30 degrees C. So what drives the flow? That temperature difference. You say to yourself, well, you're asked to calculate the rate of heat transfer from the 30 degree outside to 0 degree inside. That make sure and count for the flow through the edges and the corner sections of the box. Okay, so what we'll talk about is the faces. But we also have edges and corners. It's a little bit of bookkeeping here, all right? So maybe you think this dimension here is 20 centimeters, this dimension here is 20 centimeters, and this dimension here is 30 centimeters. You're saying, what about the 34? Well, you add the 2 and you'll add another 2, and that would give you the outside 34. But we're just looking at that layer of insulation. So one of the faces is going to be 20 by 30 as shown, but it's got 2 sides. So how many faces are 20 by 30? 2. How many are 20 by 20? 4. So this is where the engineer, this is an easy problem, but you gotta not make a mistake here, true? Well, think about it. You have this 1 here, and then on the other side 2, that's 20 by 20, right? Oh, there's only 2 of those, sorry. Yeah, you're right. There's only 2 of the 20 by 20s, and there's 4 20 by 30s, right? Even I made the mistake. All right. Those are the faces. Now, how many unique length edges do you have? You're either going to have 20 centimeter length edges or 30 centimeter length edges. How many edges are going to be 20 centimeters? 1, 2, 3, 4, 5, 6, 7, 8. And then how many are going to be 30? 1, 2, 3, 4. Yeah, so maybe I should tally this up, but you're going to have 8 edges that are 20 centimeters long and 4 edges that are 30 centimeters long. True? Now the easy one. Whew. How many corners? 8 corners. Right? 8 corners. So that's probably one of the hardest parts, just getting the bookkeeping in the right areas. Okay. Now what you do is you say, I'm going to have the flow of heat equal to Ks delta T, but I'm going to consider a bunch of entities, and I'm going to sum up over all of the entities. It can flow through with the same conductivity and the same driving temperature difference through each of those faces, through each of those corners and each of those edges. Right? So where do you get the information of the shape factor for the edge? Well, in our table and textbook, this would be case number 8, and there's the shape factor, 0.54 times D. You have to take a look at what they tell us is D for the illustration, and D isn't that the length of the edge? Right. And then what about the corner? The corner is the shape factor is equal to 0.15 times L, but, well, okay, I have to figure out what is L. What is L? It's 2 centimeters for our problem. It's the thickness of the insulation. True? All right. It's bookkeeping time, so I'm just going to show it to you like this. So I say I have a S1 dimension, which is maybe it's 20 centimeters. A S2 dimension, 20 centimeters. And the S3 dimension is 30 centimeters. So what I have is I have 2 faces that are S1 by S2 and S1 by S3, and then 2 faces that are S2 by S3. These have the 30 by 20, and here's the 20 by 20. So that's the area in meters squared. Did I do that correct? Thumbs up if you agree. Are you still thinking? Is your thumb broke? I see a lot of thumbs. Good? Is it good? All right, excellent. So what about the shape factor for those faces? Well, there wasn't a case number, whatever, 11 or something for a slab. But what was S? Area to length ratio. Area divided by the thickness. And so when we come back here, for each of these, it's just the area divided by the thickness of 2 centimeters. And you get a shape factor of 233. So look at 0.04 meters squared divided by 0.02 meter. Does that give me 2 with the units of each S has a unit of M, meter? Yes or no? All right. I think the table helps us avoid a trivial error. Okay. Then what is N? The number. You multiply by the value for each. So that's the S through that. You sum them up through all the faces, and there's 16. That's the shape factor accounting for each of those 6 faces. You summed up that part. And then you consider each edge. You have, I have 4 of them at 0.2, 4 of them at 0.2, and 4 of them at 0.3. You say, what is the S for each edge? I go back to my equation. It was 0.54 times the length. So if I put 0.54 times 0.20, do I get something close to 0.108? Yeah. It's the same thing here for the other longer length. Multiply N times S of each, add them up, and there it is, the contribution, or geometrically how it can be transmitted through the edges. Let's take a look at each of the 8 corners. The equation was 0.15 times the thickness. So 0.15 times the thickness, 0.02. Is that correct? Thumbs up if you agree. Multiplied by 8. There's the sum for the corners. I sum them up for the total system, and then I can go back and take a look. I can say, You know what? The amount of the area to length ratio, giving a geometrical pathway for heat transfer through the faces, is about 91%. 91% of the heat transfer will go through those faces. About 9% will go through the corners. Not the corners, the edges. And then what goes through the corners, the 8 corners? Almost nothing. Neglect it, right? You could neglect it. So what you do with this 17.5 is you put it in the equation. I want to know the rate of heat transfers, the thermal conductivity. We were given the thermal conductivity, so that comes down, times the S. We just calculated the S, times the delta T, which was 30 degrees C, and you get that there's a transfer of around 21 watts. It's not intellectually that challenging, but it's a challenge bookkeeping, right? All right. You ready for a clicker question? If the insulation thermal conductivity is changed from a value of 0.04 watts per meter degree C to a new value of 0.08 watts per meter degree C, how will the rate of heat transfer change? Will it increase? Will it not change, stay the same? Or will it decrease? That's pretty clever. You talk to yourself. I encourage you to sit next to somebody and talk to them, but you can always talk to yourself. We usually write the same answer. When you start arguing. All right, we're going to stop. Everybody in? All right, let's stop it. And let's see what we got. It was a straightforward question, I hope, right? What was our equation? Q equal to K S. This is the S overall, delta T. All we did was change K. We wanted it to go up. What's going to happen with Q? It will increase. It will increase. True? You ready for the next question? Ready to go? If the insulation thickness is changed from 2 centimeters, now it's increased to 3 centimeters. How will the rate of heat transfer change? Will it increase, not change, or will it decrease? Everybody in? All right, everybody's in. Let's stop it. Ed, I think we may be close to 100% correct, but somebody slips always. More insulation, lower the Q. All right, let's not lose sight of those easy things. Now I'd like to talk to you about the handout that was distributed. If you didn't get one, you can walk up here and pick one up right now, or maybe look around. There may be an extra around by your neighbors. This is a design project. I know I scheduled it later in the semester, but I saw an opportunity to put it in now. Why now? Well, because what happens at the end of the semester? Things pile up and you have 8 design projects due. I'm afraid some students are going to jump off the edge of the buildings around here at the end of the semester. Don't do that. Don't do that. But I think you may have to talk to a friend. That may have been the last one. You know what? I apologize. All right. Thank you. I'm going to post it up on Blackboard. Let's go over this. In table 4.1, case 8, the conduction shape factor through the edge of adjoining walls. We just solved that problem and used that conduction shape factor through the edge of adjoining walls. Is reported to be 0.54 times D, where D is the inside length of the edge. This is valid for a long edge compared to the wall thickness. Develop a 2-dimensional numerical model of steady heat conduction through the edge and determine an expression for the shape factor based on your results from your numerical model, and compare your numerical result with the textbook value. In other words, make some calculations looking to compute that coefficient 0.54 in front of the D and see how close you get based on your numerical model. How will you be graded? You need to have a really clearly defined mesh. 15 points. You need to show your equations before you implement them into Excel or MATLAB. I need to see them written out. You say, that's pretty tedious. Do it. Do it, do it, do it. 15 points. You need to have readable Excel code. If I look at your equations the way you wrote them, then I look at your Excel code, I should be able to understand the implementation. Okay? And you need to clearly have a solid method for how you're computing S based on those results. How's that shape factor right here? How are you going to compute it based on your results? That needs to be worked out on paper and then implemented in Excel. So I'm going to be looking for some hand verification calculations, not of every step that the Excel is going to do, but of some. I want at least one check on a node balance done by hand and shown that it verifies what is in Excel. Just one, not every one, just one. And then you make the comparison and make some observations about how close your results are. And then you have to email the code to me. And right down here is where you email it. So it's worth 10 points just to email the code. I mean, it could be junk. Just say, empty code. You got 10 out of 100.
How do you want this presented, source format, like paper-wise?
I prefer the hand calculations, but some people like to type them, and you're going to see where I type some things just like what I asked for. And so I will demonstrate that in a few minutes.
I mean like report format.
If you want to put a nice cover sheet on it, perfect. You don't need an abstract and conclusions and introduction and stuff like that. So it's pretty simple. If you want to show me what you got before you turned it in, I'll be fine to look it over, but I'm pretty relaxed on that. All right? Any other questions? Yes, sir.
On the Excel code, do you want to see the functions or just the
Yeah, I used to have them where you did the Control-Alt something and then it showed the functions and print it twice. No, because I'm afraid they could be a little long. So just you're going to show me the code, print the sheet showing, like right here is a print of my Excel sheet, okay, for a problem. Attach that, but also send the code. All right, but you don't have to print showing formulas. Thank you for asking that. Yes?
Could you clarify define mesh?
Yeah. Some people may do it with 11, 12, 20, 30 nodes. You've got to show me your nodes, your mesh. I'm not saying there's a minimum, but I'm saying don't get ridiculous on the number of nodes. Okay? If you're starting to push 100, you're out of the league. You probably should be below 50. All right? 5 nodes. Nah, it's not going to be good enough, I don't think. Yes? Somebody else? All right, let's continue on because I want to demonstrate solving a problem similar to the problem that I've asked you to solve. But it's not that close that you can just reproduce it. So here it is. Consider a two-dimensional straight triangular fin of length 50 millimeters. So here's the 50 millimeters. And a base thickness of 20 millimeters. The thermal conductivity of the fin is 25 watts per meter K. The base temperature is 50 degrees C. Where is the base of this fin? You have 3 choices, here, here, or here. The third one. Yeah, so all along this is the base, and every one of those nodes have a temperature of 50. That's the constant base temperature. All right. It's exposed to convection fluid with the convection coefficient H and the temperature of the fluid of 20 degrees C. Using the finite difference mesh with delta X equal to 10 millimeters. Let's go through this delta X. You set up a line, a constant X. Set up a line at constant X. Line at constant X, line at constant X, line at constant X, line at constant X. I know that line, that last line only has one node on it. But each one of these lines is 10 millimeters wide, the distance between them. So you get 10 plus 10 plus 10 plus, isn't that 50? Doesn't that make sense? And so nodes 1, 2, 3, 4, 5, 6 all are at x equal to 0. 7, 8, 9, 10, 11 are at x equal to 10 millimeters, 12, 13, 14. I'm belaboring a point here, okay? But we're clear about that. Now, the same thing here, you're going to exploit symmetry. So I can cut this in half, and I can treat that top half as being the only half I have to analyze, because if I flip it over, the whole system's symmetrical. So thermally, this is like being an insulated boundary condition on the bottom of the top half, true? Thermally, it's like being insulated. True. That's a symmetry boundary condition. So all we have to do is go 10 millimeters, not the full 20, in our mesh. And so if you go every 2 millimeters, 2 millimeters, 2 millimeters, 2 millimeters, 2 millimeters, you traverse the whole thing. So our delta y is 2 millimeters. That makes sense? All right. What they want you to do is numerically solve for all of the temperatures in the mesh. So I have 21 nodes. I want 21 temperatures. The first 6 are pretty easy because they're equal to 50, the base temperature. So there's really only 7 through 21 that I really need to calculate. They're the unknown temperatures. Once I have them, then I can compute something, an abstract concept like the fin efficiency. Professor, how are we ever going to compute the fin efficiency? This is the type of thought process you need to go through, just like I asked about the conduction shape factor. You need to think a little bit. Well, what was the fin efficiency defined as? It's the rate of heat transfer off of the fin into the fluid, actually for the case, the real fin, compared to some maximum theoretically impossible to achieve, but hey, it's our maximum. And what was the idea behind that maximum? Exactly. The entire fin everywhere is exactly the same as the temperature of the base. Could you calculate Q max? And if you could calculate Q max, then I think you know now how to calculate Q actual from the numerical results. Remember, do you think the temperature out at 21, do you think it's going to be greater than 50, equal to 50, or less than 50 degrees C? Less. The fluid's at 20, it'll be between 50 and 20. It would be ridiculous to be less than 20 or greater than 50. So what you do to get the maximum, you say, I'm going to sum up how much heat comes off of this part into the fluid, plus how much heat comes off of that part into the fluid, how much heat comes off of this part into the fluid, how much heat comes off of that part into the fluid, how much heat comes off that part into the fluid, and then off this part into the fluid. See that? Won't that give me how much heat is being transferred from the fin into the fluid? And if I'm interested in doing the maximum, each one of those nodes, the 6, the 11, the whatever that number is, 15 and 18, I think, and 20, they all have 50 degrees C. That's how I'll calculate the maximum. So basically, it'll be the convection coefficient times the area for the 6th node times the temperature of the 6th node minus the temperature of the fluid, plus the convection coefficient times the area of the 11th node times the temperature of the 11th minus the temperature infinity of the fluid, plus the convection coefficient area of the 15th node times the temperature of the 15th node minus the temperature infinity of the fluid, plus convection coefficient area of the 18th node. Why do I put a parenthesis there? I have no idea. All right, temperature of the 18th node minus temperature infinity. Let me finish it out. Area of the 20th node, temperature of the 20th node minus T infinity, plus the convection coefficient area of the 21st node times T infinity. T21 minus T infinity. Did I do that right? Finally. Each one of these areas is a product of, let's try and draw it in 3D. In 3D, it goes back W or Z, delta Z. But guess what? W or delta Z, think about it being a unit meter length. delta Z or W being 1 meter. So everything's going to be for a 1 meter depth per unit meter depth of my triangular cross-sectional fin. That makes sense? All right. So each one of these are just going to be a product of some sort of length. Now, here, little quiz. What's the length between node 15 and 18? It'll be delta x of 10 millimeters horizontal run with the 2 millimeter vertical run, giving us hypotenuse. I'm going to call this is delta x, that's delta y. I'm going to say dl is equal to delta x squared plus delta y squared square root. True or false? True. So it's a little bit more than 10, isn't it? Just a little bit more than 10. So this will be dl times, let me say 1 meter depth, and then you divide by 2. Why do I need a dl over 2? Because area of 6 goes only half the way. The area of 11 is a full dl, isn't it? And the area for 15 is a full dl, and the area of 18 is a full dl, and area 20 is a full dl. But what about the area of 21? Half dl. True? So once you have that, that same equation works both in the numerator as well as the denominator. For max, what do I put in for all of these temperatures? 50 degrees C. For the Q actual, what do I put in for all those temperatures? Got to go and solve for them numerically. Once you solve for them numerically, you compute it. As long as we have a good roadmap of what we're doing in our mind, now it's pretty straightforward. So, with the paper that I handed out, I want you to look at it and understand why I put those blue lines in, those lightly blue lines. Well, they go halfway so that the boundary between, let's say, node 2 and node 8 is right in the middle, isn't it? And then between node 8 and node 13 is right in the middle. And between and then between 2 and 3, right in the middle. So those lines that separate, and what they do is help me clearly identify what real estate belongs to each node. So the real estate that belongs to node 8 is everything in there, isn't it? Isn't that true? All right, now it's hard to see, so I get rid of it. The real estate associated with node 1, isn't it this? What's the real estate associated with node 6? Just a little piece of property, right? And down here for 20. Right? All right. Now, I picked a node. I picked node 11. What I want you to do is write the energy balance for node 11. I'm going to stop, I'm going to walk around and see how you do. Because if this is you need to do, then you're going to implement that into either MATLAB or Excel. You'll not only have to get the energy balance for node 11, you'll have to do it for 10, 9, 8, and all those nodes. Each one of those nodes needs an energy balance. And I need that as part of the design project. Remember we talked about the design project? Wasn't it 15 points for that part of it? All right, I'm going to pause, walk around. All right, so here it is. If you're going and you need to go across a floor that's just been mopped and it's very wet and slippery, you need to go from point A to point B. You could have one of two strategies. The less time I spend on that floor, the lower the probability of me slipping and getting hurt, so I'm going to run. That's option A. Option B is I'm going to have to go slow and take baby steps. If I take baby steps, then I'll lower the probability of slipping, hurting myself. Which is the better option? A, go real fast, and then, yeah, no, it's not especially if there's a corner right there. And then, okay. But the same thing holds true in a lot of things. go slow. Right here, somebody put a little diagram and they said, you know what? Something comes into the node, something comes into the node, something comes into the node. He had 3 things he needs to count for. Some people are like, oh, I'm just going to count for 2 of them. I forgot one of them. So what do they have? Conduction from 5 into 11, conduction from 10 into 11, convection from T infinity into 11. Those 3 things. This is how I'd write it because I don't like to slip on floors. I'd write it like that. The first line, I'd say the conduction from 5 into 11 plus the conduction from 10 into 11 plus the convection from T infinity, the fluid, into 11 must all sum to 0. Now, I'll hand it to you. There's a lot of you that say, I think I got this in one fell swoop. I wouldn't. I'd go slow. Because what do you know when you look at 5 into 11? We know we're going to apply the equation that the amount of heat transfer from 5 in there is going to be the thermal conductivity, T5 minus T11. That's nice, right? But here's the tricky spot right there, right? What is my area going from 5 into 11? Delta Y over 2 times delta Z, which we said we're going to leave to be 1 meter. So if you left it out, that was fine. Now I have to divide by the distance. What do I divide by for the distance between 5 and 11? Delta X. Why are we doing over 2? It's not over 2, is it? It's delta Y, delta Z divided by delta X. I was thinking of another case. Sorry. Yeah, it's good. Yeah. No, it's a full delta Y area. All right, what about 10? Q10 into, it'll be T10 minus T11. Get the temperatures right. The thermal conductivity, no problem. The area, in this case, will be delta X. I know I'm going to leave out the delta Z. Just put the delta Z equal to 1. Time divided by the distance, delta Y. So I think, Frank, you had it right the whole way, didn't you? Very good. All right, now, what about the convection? It was H times dl or delta L or whatever. I know that we introduce another symbol. I have delta X is this much, delta Y is that much. dl is equal to 2 squared plus 10 squared square root, so many millimeters. I like to use that as a symbol. So I'm just going to multiply by dl or delta L times, it's coming in, so it's T infinity minus T11, isn't it? Or is it T11 minus T infinity? Which one? Not arbitrary, because it's a plus coming in from T infinity. So this is the way you have to write it. And if you put a minus sign here and a plus sign there, well, you just introduced an error. Well, I think Excel is so smart that numerically it'll correct any of my errors. Is that true? MATLAB, Excel? No, the computer's just going to do exactly what you told it to do. And when it bombs, you just know, oops, I told it to do something I didn't want it to do. So, isn't this right? Look okay? Thumbs up if you agree. All right. Then the last thing, what I would do is I'm going to have to put this in a matrix format. I need to put it in a matrix format. And in the every equation that I'm putting in will be one row. And so what I do is I sort them out and I put the entries first. Like T5 comes first because it's the lowest number of the node, then T10, then 11, and then anything that's not multiplying one of my temperatures, 1 through 21, goes over on the right-hand side. I got to go slow or I'll make a bunch of errors, okay? So this is my coefficient that multiplies T5 from my energy balance equation, the coefficient that multiplies T10. I know that all of them are going to be negative that multiply, that's a plus right there, isn't it? Yeah. That multiply T11, so I just put the negative sign outside in the big parenthesis, these three parts. And then everything that doesn't multiply one of my T1 through T21s, I put over on the right-hand side. Make sense? I want to see this for every one of your nodes in the mesh that you're going to turn in for your project. Why can't we just implement it? I want to see your hands derive it. All right, after solving for all the t's, we already talked about this. How do you calculate the q? You get the q two ways you could do it. One way, not recommended, conduction going into from nodes 1, 2, 3, 4, 5, 6. I don't recommend that. I recommend the convection from 6 and 11 and 15 and 18 and 20 and 21. And we already wrote that equation, and there it is, right? That's the equation. So we have the area dl over 2 for the area 6, and then a full dl and a full dl for 11 and 15 and 18 and etc. half for 21. That makes sense? All right. But I have to calculate those temperatures. How do I calculate them? Set it up in a big matrix format. So this is my setting up Excel to solve this problem. Let me turn my computer around a little bit. Yeah, too many lines. Oops. All right, we'll give it the best shot we can. So first things first, I'll use multiple screens, or what do they call these? Tabs, multiple tabs. I'll put a tab just to say, here's my information that I set up the problem. So I put in K and H and base temperature and infinity. And you know what? Later when I come back, I could actually change those. It'd be pretty automatic. The next thing I do is I define things with names. Because when I go to the next sheet, I just want it to go and get it from another sheet, and I don't want to deal with it. So I've given the name COND for this parameter 25. How do I do that? Well, let's say I introduced the parameter 33 and I wanted to give it the name ABLED, enabled. Anyway, it did it for abled. I don't think I spelled abled right. But anyway, I did that up here for COND. That's conductivity. When I want it, it'll go get it. How many people have used names? Couple. Good. Consult the experts. They just volunteered by putting their hand up. Now, the next thing is I need to spend time making this big A matrix. There's 21 nodes. I recommend you have 21 by 21 big A matrix. All right? Now, the first 1, 2, 3, 4, 5, 6 rows are trivial. All it is ones on the diagonal, and when you come over here in the B, you just put the value of the temperature it's supposed to be. Let me do this quickly. Escape. Skip that right out. You don't see the solutions. That's where I'm going to Excel is going to calculate the solution. True? X. AX equal B. Now I put in some of these that are non-zero coefficients. I somewhat color-coded them just a little bit. So if I take a look, here's the 11th. You just worked it out. Then you do the energy balance for the 11th node. This line right here is the energy balance for the 11th node. It plays with node 5. Can you see that? So when I evaluate that coefficient, what was that coefficient again? Escape. Hit it. It's right here. Conductivity times dy divided by dx. Wasn't that the coefficient in front of T5? And then over here, what's the coefficient in front of T10? Conductivity times dx divided by dy. So I have it so I can read it. I can debug it. All right. And then over here I have the T infinity times dl times convection with the minus sign. True? All right. So I've implemented in there. Now, what you do is you put the B, A, and B all in there. Now you select the A array that you want to put the solution in. I just selected it. You then type equal sign. It'll only go to the first cell of that array. And you type what I've said down here, matrix multiply. And if you have any questions about it, just hit the function key and then it tells you all sorts of things about it. But right now, I want to do the matrix multiply of the inverse of that big A matrix. Matrix inverse of the big A matrix. Not only did I give names like COND or other things, I called that BIG, and you can see it's starting to say, what big do you want? Big A? Hit tab. So I named that matrix as big A, hit parenthesis, comma. So it calculates the inverse of big A, and then I multiply that by big B. You have your own style, okay? You have your own style. But at this point, if I hit enter, no good. Hold shift control, hit enter, and it solves for it. So the temperature at node 21, which was way out at the tip, is 39.086 degrees C. And the temperature of all those nodes are known. So I have a whole thing. The other one is, in debugging, you probably want to check that's what the A inverse looks like. It's not too pretty, is it? But there's the inverse of that big A matrix. Forget it. Let's press on. I then put in one spreadsheet the solution. So I said, I'm going to have to tally something from 6, 11, 15, 18, 20, 21. Let me go get the temperatures. Well, I indexed, go get the temperature, the sixth one out of that array. That's what I'm doing with index. So I just pull those temperatures, and then the delta T between that temperature and the fluid is calculated just by subtracting T infinity. I know the length of the line, dl divided by 2. This one's dl, 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 dl over 2. And then I have what is the h dl times dt, how many watts per meter length, depth. Comes off of that from node 6, from node 11, from node 15. I sum them all up. I get 61.964 watts per meter. Make sense? So actual is 61.96 watts per meter. What about the maximum? Well, the maximum's kind of easy. You just take the delta T at the base, 30, times the whole length, times the convection coefficient, and it comes in at 76. I take the ratio for the efficiency. Professor, you only did it for half. Okay, double everything and do it again, you'll get the same number. It's not going to change efficiency. So 81%. The textbook actually has a figure where you can back out an efficiency for a triangular fin. It shows it coming graphically to be around 78%. Is that a perfect match? No, but it's pretty good, isn't it? Thank you for your attention. We'll see you next time. We're done with this chapter.